So today, at 1 o'clock, starting at 1 o'clock, we're going to be assembling the robots in the lab for use in this class. And we thought it would be an enjoyable and valuable experience for any of you who would like to come participate in that. You're not required to by any means, but I think you'll get a deeper insight into what's there and why it's there if you do participate in that. And if you've never done any soldering or wiring, this would be a good chance to learn from a pro how it's done right. So you can figure out which end of the soldering iron is the right one to hold. So that's pretty easy to learn, by the way. So yeah, it's not a huge assembly job. So the whole thing will be over pretty quickly. So be there promptly at 1 if you want to participate in this. Okay, so today we're talking about memory models. Does anybody have any questions, by the way, logistics or, yeah?
When we're talking about this architecture,
Mm-hmm.
we have 16 bit
16-bit address in this architecture, that's right. So that's a very good question. So does that mean that it takes 2 cycles to execute one instruction? Actually, in this architecture, it doesn't. What it means is that the data bus itself is 8 bits, but the address bus is 16 bits. And so the program counter is 16 bits. And so in one cycle, it puts the program counter address onto the bus. And the instruction word size, actually, I think the instruction word size in this architecture is also 16 bits. So the program memory is separate from the data memory. Actually, I'm not totally sure whether that's true in this architecture. That's so a fairly typical architecture is an architecture called a Harvard architecture, where the program memory and the data memory are distinctly separate. The reason it's called the Harvard architecture is because way back in the 50s, in the days when very few institutions had computer installations, Harvard developed their own rather weird architecture that everyone thought was really strange because it had the data memory and the program memory separated, and so it became known as the Harvard architecture since then. But if you have a Harvard architecture, your data word size and your instruction word size need not be the same. They can be, the width of your interface to the memory determines whether they're the same or not. So in a Harvard architecture, you would not store instructions in the data RAM. So you could be fetching 16-bit instructions in one cycle and 8-bit words in one cycle. If you have an instruction that has an immediate address in it, then it may take 2 cycles to execute that instruction because it may take two locations to store that instruction, right? If it's a 16-bit instruction word and it's a 16-bit address, then it takes 16 bits to store a single address. So the read immediate that specifies an address is going to take 2 instruction words to store, and so it'll take 2 cycles to fetch that. But on the other hand, if the address that you're reading from is specified in a register, then a single 16-bit instruction word can specify the register, and consequently it becomes possible to execute that instruction in one cycle. But now that you mention it, I'm not sure whether the program memory in this architecture is 8 bits or 16 bits. If it is 8 bits, then yes, I think most instructions would take 2 cycles to execute. But if it's 16 bits, probably most instructions take 1 cycle to execute. This sort of topic, does this get covered in 61C? Kind of? I've never taught 61C, so I don't know in depth what they cover. I've looked at the syllabus, but it seems like that's what I would expect them to be talking about there. Okay, so in this case, we've been focusing on the data memory pretty much exclusively and not the instruction memory. And the data memory, to remind you, is laid out like this. It's got a 16-bit word. In this particular architecture, this particular implementation of the architecture, there's only 1K of data RAM, and that's mapped into the addresses starting at location 100 in hex. So it goes up from 100 to 2FF in hex or 4FF. So if it's 1K of memory, it looks like in one picture they've shown two variants, either 512 words or 1024. So if it goes up to 2FF, is it 512 words or 1K? So 2FF minus 100 hex is 1FF. What's 1FF in decimal? It's 511, right? So the addresses would be 0 to 511. So if the RAM goes up to 2FF, then you only have 512 words. If it goes up to 4FF, then you have 1024 words or 1 kilobyte. Okay. It's useful, by the way, when you're working at the low level of architectures to kind of get used to reading hexadecimal, because it's a far more convenient way to specify addresses than decimal numbers. Okay. All right. So we were looking at the memory model in C, is really what we're looking at the moment. How does the C programming language use memory? And this particular program has these variables here, which are called automatic variables. The memory is allocated on the stack when the when the procedure gets invoked. Okay, so these variables exist only during the execution of this procedure. The memory is allocated on the stack, and consequently, when this procedure returns, that memory is effectively freed and can be overwritten by something else, another procedure call, for example. The variable x is a pointer, so because this architecture uses 16-bit addresses, this pointer will occupy 2 bytes of memory. This variable is not a pointer, it's a data reference, so it's declared to be a char, which is in C defined to be a single byte, and consequently it'll occupy 1 byte of memory on the stack. X is getting assigned to 0x20, and don't be misled by the fact that only 1 byte has been specified here. This will assign a 16-bit number to X. Okay, it's up to the compiler to make sure that happens, by the way. Okay, but the compiler in C, the compiler will take care of that, right? There's many ways to express numeric constants in C, but the actual value of the numeric constant depends on the data type. Okay, so in this case, the data type is a pointer, which will be a 16-bit number in this architecture. Y will get the value of the memory location 0x20, which in this architecture is simply the first of the 64 I/O registers. So if you have an external device, right, that you've built, you've wired up some piece of hardware, and you'd like to convey to your program some information from this external device, one way you could set this up is simply hang your device off the bus in such a way that when the address 0x20 appears on the bus, it asserts your value on the bus on the data lines, and bingo, your C program can read that value and assign it to a variable and operate on it. Okay? So that's how I/O works in this context, and you'll see in the lab, certainly this week I think you're already doing this, you're reading and writing to absolute addresses in order to interface with I/O devices. Okay. Typically, the manufacturer of the board tries to make your life a little bit easier by giving you symbolic names for these addresses. So normally, you wouldn't write a C program that says x equals 0x20. You would write a C program that says something like, x equals AD0's status register. Okay? And this is defined in a header file somewhere to have value 0x20. And the reason they do that, of course, is that then, if you upgrade to a different processor that happens to maybe have more registers, consequently this address would have to change, you can still recompile the same C program and it'll still work. Okay? So you want to use symbolic numbers. You don't want to, in general, programmers call something like this a naked constant. And that's a disparaging term. You don't want naked constants in your code. Okay? Use header files, define symbols, and put, anything that's architecture dependent, you want to consolidate into one little small table, okay, of definitions. Yeah, question.
So like in this architecture,
What's your name?
Nima?
Nima.
Yeah. How do we like characterize integers? Because like our bus is like only 8, so if you have an integer, how does it?
Well, one of the glories of C is that it doesn't actually define what an int is. Okay, so it's kind of up to the compiler here to decide what to do for this architecture. So you've got to read the documentation to find out what an int is. It might tell you that an int is a 32-bit number, in which case, if x was an int, it would take 4 cycles to load a constant into the memory location for the int, because it would be 4 bytes that have to be written into 4 successive locations. One of the challenges, by the way, with writing low-level C programs is getting things aligned properly, right? Because if you're operating on individual bytes, some of the words that you write stretch over multiple bytes, and so you have to be able to sometimes figure out what is the correct address for things. And you need to know the word sizes generally. So in my view, it's a real weakness in C that they didn't have the backbone to define an int, but that's life. Okay. So the other thing that's going on here is that the Z variable is not on the stack because it's declared outside of any procedure. So that's called a static variable, and that will be assigned by the compiler typically to a location early in memory. And the stack will start late in memory, okay? And the stack will grow upwards or downwards in address, upwards in this picture, and hopefully will not overwrite your static variables, because if it does, the program becomes extremely difficult to understand. By the way, that's a really popular way to write viruses. Okay, you can actually, if you write code that manipulates the stack in wacky ways, you can make computers do amazing things that nobody ever wanted them to do. Okay. All right. Here's a variant of this code. Here, I think one of the reasons I wanted to show you this is just there's a lot of data types in C that try to correct some for the deficiencies of the C definition language. So this one right here, the way to read this is an unsigned int with 16 bits, and the underscore T is just a reminder that this is a type. Okay? So this is a particular int where now we have asserted this is a 16-bit int. This is not just a C int, which could be anything. Okay, this is a 16-bit integer, and moreover, it's unsigned, which means that there's no interpretation to the sign bit. It doesn't care. It's just 16 bits, right? You can interpret it as a positive number. You can interpret it as just 16 bits. Okay. So in this case, when you assign a value to x, this is assured of being a 16-bit value, and you can dereference this simply because you know that this is a 16-bit architecture. Okay? If you try to do this same thing on a 32-bit architecture, you're going to get into trouble. Okay, but C is not a strongly typed language. C lets you play fast and loose with data types, and so it's kind of useful to, when you're programming in C, you're really controlling the machine at the bit level, and that's one of the reasons that we want to use it in this class. Is we want you to get that feel of controlling the machine. But you know, if you're writing application programs for PCs, you don't want people controlling the machine. That's generally frowned upon. Okay, so what else was there in here? Oh, so let's look carefully at what this does. So what does this procedure return? Where is the return value stored? Sorry? Yeah, Z won't be on the heap. Okay, Z is a static variable. So the compiler will simply allocate a location here that will not be accessible to the heap. The heap is what is used by when you dynamically allocate memory using malloc. Okay, in C. That's your compiler, your implementation of malloc has to ensure that it doesn't assign locations that were already assigned to static variables. Okay, that's part of the trick in implementing malloc correctly. But Z in this case will simply be a static variable, so it's just a hard-coded address. Okay, so what's going to happen is that this will put the return value temporarily on the stack. So it'll read the value of the register at location 20, stick it on the stack. Part of the return operation will then be copying that value from the stack into that static location. Okay, and after this line executes now, the stack pointer now will point to below the location where that variable, the return value had been stored, the Y variable had been stored, the X variable had been stored. The stack pointer is now below all of those, okay? And the returned value is now in the static location, which is probably here, okay? And the next time you make a procedure call, you will go ahead and overwrite those variables that had been stored on the stack. Okay? By the way, that's another trick you can play in C, is that if you know that another procedure has not been called, you can take a look at the stack register and read all the values that the previous procedure call used temporarily. Okay, a lot of sneaky tricks you can play, and people love to do that to make malware. All right, so here's a program that has a flaw. So I'd like you to look at it for a minute and tell me what the flaw is. First of all, does anybody not know what the ampersand operator means in C? You don't? So it means it means this is the address of the variable Z. Okay, so the value of this is a 16-bit number in this architecture, which is whatever address Z is stored at. Okay? Yeah. Sure, yeah. What's your name? Oren? Right. So what will the variable result? What's the value of the variable result here? Sorry, what? You're Bailey, right?
It points to the address in the stack, and that value holds 20.
So the value holds 20. Why?
In 2 cents.
Uh,
The address is not defined, but the value is.
oh, right. I see. Right. Of course. Yeah. Okay. So we're calling foo with value 10. So y will have value 10. X is a static variable with value 2. So we assign z the value 20, and we return the address of the location that stores that value 20. And then result has what value? Does the result have the value 20? No, it has the address that stores 20, right? But that address is on the stack, okay? So if you use that value immediately, before anything else gets done to the stack, you may be okay. But is that safe to do? Why not? Yeah, if you're multi-threading, definitely not. But multi-threading is an operating system level concept. We don't have an operating system here. This is bare iron. Sorry? What if an interrupt occurs? Okay, interrupt is a bare iron concept. By the way, it's how multi-threading gets implemented. Okay, so interrupt is a more primitive concept. But the issue is that at any time, a C program can get interrupted. And what happens when it gets interrupted is your current location of the program counter gets pushed onto the stack. By the way, that'll probably overwrite the value 20, okay, immediately. And then any registers that the interrupt service routine uses also get pushed onto the stack, their value. And then an interrupt service routine executes. And then all those register values get read back off the stack and put back into the registers. And then the program counter gets restored, and then you resume executing where you left off. So if you have any interrupts at all enabled in your program, then between this instruction and the next, you have no assurance that the stack was preserved. Okay? It's even worse in C because there's no notion of from one instruction to the next. You can't count on a single instruction in C executing atomically without being interrupted halfway through. Okay? You can't even count on a single assembly language instruction being executed all the way through. So if, for example, you have a multi-cycle instruction, you have an 8-bit processor, it's working on 16-bit numbers, you could get interrupted halfway through writing a value into a 16-bit variable. Okay? So you really sort of, I mean, you can really mess things up if you write programs like this where you're counting on things being on the stack. And the worst thing is, when you use the usual programming technique that everyone does, which is you write code, you try it, you see if it works. If it works, you declare success, you turn in the assignment. It'll probably work most of the time. But it'll fail at the worst possible time, right? Which in my experience is always when you're giving a demo to the sponsor. That's when it fails. Okay. All right. So let's decompose this to make sure everyone understands. So this variable x is statically allocated. The compiler assigns a memory location. The argument is pushed onto the stack. The automatic variable is allocated on the stack. The program counter and copies of all of the registers go on the stack when you make a procedure call. Okay. The program returns, in this case, a pointer to a variable on the stack. And if you then dereference that pointer later, the value of that variable could be just about anything. Okay? That's the point. All right, so here's another program, and I'd like to know what the value of z is after this executes. Been a while since I've looked at this, so I'm actually not sure what the answer is. Sorry? Yeah.
I'm not sure, but I think
NEMA?
that- Yeah. I think maybe like you call the function foo is gonna like write throughout the whole memory, and then it's gonna override the value of z as well.
Right.
It's probably gonna be like one of the variables like y or
It might be a variable y. It might be the program counter at some point. It could be just about anything in this program. Okay? I mean, if you look at this program, you would say, well, yeah, z would have to have value, hex 10, because the procedure foo doesn't take z as an argument, doesn't operate on z, doesn't do anything with z. Shouldn't mess with the value of z. We only have 1K of memory, though, in this architecture. And we've done a recursive call at least 100 times in hex, which is big enough to overwrite the memory. You're going to get a stack overflow. It's big enough, actually, to write to the I/O registers, too. This program probably won't even complete execution. It's going to start doing just crazy stuff. As soon as your stack exceeds where the program counter is stored, okay, you're going to overwrite the program counter when you make a procedure call. Yeah. Yeah, foo itself doesn't modify memory, but every time you make a procedure call, your program counter gets pushed on the stack, your argument gets pushed on the stack, so at least two 16-bit words, that's going to be, 4 bytes are going to get pushed on the stack every time you call foo, at least. And the compiler is free to put more stuff on the stack for optimization purposes. It might put register values on the stack. Okay? Sorry? Y goes on the stack as well. That's right, the automatic variable. So that's another byte. So each time foo gets called, you're going to push a whole bunch of stuff onto the stack, which is going to decrement the stack pointer. So every time foo gets called, the stack pointer is going to get decremented until eventually it overwrites the value of z. And this will be big enough, I think, to overwrite the external I/O registers and on up. Okay. So you can get chaos very quickly in these programs. All right. So that was an 8-bit architecture. Here's a slightly more sophisticated architecture. This one is closer to the one that you're using in the lab, but not exactly the same. I couldn't find as good a summary picture of the one you're using in the lab. I'm still looking for that. But this is the one we used the last 2 years in the lab. It was an ARM processor. ARM is, by the way, an interesting company. They sell almost exclusively to embedded system companies. And they're actually what is called an IP company. They don't actually make silicon. They sell the intellectual property. They have defined an architecture or a family of architectures. And they license those designs to people, and they sell the software that supports the architecture, the compilers, the development environments, and so on. I met the chief technology officer of ARM, and he told me that they have shipped 12 billion ARM processors. Okay, that is far more than Intel has shipped x86s by several orders of magnitude. Okay, I mean, way more. All right. He says that a modern cell phone has at least 5 ARM processors in it. Okay, plus there's dozens of them in a typical car. They go into the airbag system. They go into all kinds of stuff in the car. So, there's a lot of them out there. It's kind of a big thing. So ARM processors are out there in force in embedded systems. And this Luminary board that we used the last 2 years had an ARM processor in it. And this is a picture of the architecture. So there's a core, which is the processor itself. Does anyone know what JTAG is? You've used it in the lab, even if you didn't realize. Nima?
connection, like parallel or serial, but it's a bit different.
Yeah. So what it is, if you think of a processor is a collection of a whole bunch of stuff. It's got registers in it that, these registers are visible to the program, but it also has registers that are not visible to the program, which are just latches in the circuitry, okay? And a whole bunch of state. So JTAG is a serial interface where you can stuff a sequence of bits in and take a sequence of bits out, and it weaves through all of the latches and registers in the architecture and comes back out. Okay? So basically, if you count up the total number of bits in registers and latches in the processor, it's several thousand, tens of thousands of bits maybe. You give it a sequence of tens of thousands of bits and you fix the state of the processor. Okay? Then you release the processor to start executing. At any time, you can then stop it and read back the whole state of the processor as a sequence of thousands of bits. This is how a debugger works. Okay? The way the debugger works is, you start your program, and you control it so that it executes exactly one cycle. Then you read back the entire state of your processor, and your software takes that sequence of several thousand bits, figures out which ones correspond to this register, which ones correspond to that register, and so on, presents that all in a nice GUI to you, showing you what the state of the registers of the processor are, and then allows one more cycle to execute, and then reads back the state of the processor, and so on. The way breakpoints work is simply that it reads back the state of the processor, and if the state matches the program counter, if the program counter matches the location that you want to set a breakpoint at, then it stops execution. Otherwise, it allows execution to continue. Okay? So one of the things I really want you guys to be doing in the lab is thinking through the mechanisms that make things work. It's too easy to say, well, all right, a debugger is just something that shows me the state of the processor, and I click and it executes one cycle. How does it know the state of the processor? Right? That's the kind of question, I think, in order to really do effective design in an embedded system context, that's the kind of question you want to be asking all the time. How does it work? Right? The state of the processor is not exposed as a whole bunch of pins. It would take too many pins to do that. Right? You just don't have that many connections to the processor. It's a single serial line. That's what JTAG is. Okay? So it's a very powerful tool because it also means you can do crazy stuff like run programs backwards. Okay? You just keep a record of the state of the processor in each step, and you reach a certain point where you say, oh, geez, what happened 4 cycles ago? Let me back up. Right? As long as you stored the state of the processor, you can restore it to that point 4 cycles earlier and look at what happened. Okay? Very powerful tool. Okay, so the core of the processor is pretty Spartan. It just has the registers and the instruction set and so on. There's no I/O that's part of that. Then it has a whole bunch of interfaces. The UARTs are, in some sense, the simplest ones to use in hardware. In software. They're serial devices that were originally designed to work with teletypes. Okay, it's that old. The UART mechanism was designed way back in the 50s so that you could connect teletypes to computers. Teletypes had been around longer, right? They were used in the 30s to send telegrams, and they were cheap relative to other terminals that you could use for computers, and so it was very convenient to be able to connect a teletype to a computer. So people figured out how to do that, and the result is something called a UART. Yeah. Remind me of your name? Ryan, thank you.
How are these buses adjudicated?
Yeah, that's a good question. So the question was how are the buses? How do you do the media access control for the buses? That's the technical term, right? Because you have a whole bunch of devices wired up to the same piece of wire. how do you keep them from colliding with one another? I'm gonna talk about that in just a minute because we're going to talk a little bit about the circuitry of I/O. Okay, and it is important to know how that works. So UART is a serial port interface. You can use UART to connect to Bluetooth. That means you can very easily get a serial port connection over a wireless link. It's a nice thing to do in lab exercises because it's relatively easy to do. It's you know, if you want to get a wireless connection between two embedded system devices that don't have an operating system, using the serial port through Bluetooth is much easier than writing a TCP/IP stack on Wi-Fi. Okay, much easier. So that's what's used, by the way, in the Wiimote. Okay, it's the Wiimote communicates with its base station through Bluetooth, and in the base station, it's just using a straightforward serial interface to access that Bluetooth information. By the way, the trends in interfaces are very strongly towards serial interfaces rather than parallel interfaces. It used to be that, you know, for example, in the old IBM PCs, you had a serial interface and a parallel interface. A parallel interface was often used to connect to printers. It was, you know, a very common one that was used was called a Centronics parallel interface. It has a whole bunch of wires, big connector. SCSI is another parallel interface that's used to connect to disk drives. These things are rapidly becoming obsolete. Why? I mean, parallel interfaces use lots of wires to communicate. Serial interfaces use typically 2 wires, or in the case of USB, 4 wires. Okay? Why wouldn't this be better? Lots of wires has got to be better than 2 wires. Yeah? Actually, so the speculation is that the programming is easier for the serial interfaces, but actually it's the reverse. Programming is easier for the parallel interfaces because if you have, you know, say you have a 32-bit architecture, if you have 32 wires, you just write to them a word, right? Bang, out it goes. If it's a serial port, you've got to figure out, well, all right, are you gonna send the low order bit out first or the high order bit? What if you get it backwards? How do you shift out the bits? Right? So it's actually a little bit harder with the serial interface. The software is a little bit harder. Yeah.
It's more expensive because the connectors, the cable.
Yeah.
Because you'll get kind of neutral capacitance parallel.
So you've given 3 excellent reasons, right? Those were 3 reasons. So the first one was the connectors and the wires are more expensive and bulkier and harder to work with. And the second one was that you can't run them at as high a speed because there's intrinsically more capacitance in these connections, partly as a consequence of there being more wires bundled together. And the third one is synchronization problems. The third one, it turns out to be the killer one, okay? It used to be that you were willing to pay the price of more expensive connectors and wires because the performance was better on parallel connections. The serial connections have gotten much better, and they actually outperform the parallel connections these days because the synchronization problem is that if you assert 32 values on 32 wires, at the receiving end, you want to latch those at just the right time that you see exactly the same 32 values, right? Well, what if the propagation delay on this wire is a little bit slower than the propagation delay on that wire? Okay? Then you have to slow down the rate at which you latch these things enough to compensate for that. And it turns out that the performance has gotten to the point where those differences in propagation delay limit the performance of parallel interfaces. And serial interfaces, you can crank the rates way up and you don't have that synchronization problem. Okay? So serial interfaces turn out to be technically better for many reasons, even though it's slightly counterintuitive because you would think more resources would be technically better than fewer resources. It's not always that way. Any other comments or questions? Yeah. Yeah, so you could take a parallel interface and just use every wire as a serial interface. That would really complicate the programming, but yes, that might be a way to take advantage of more wires. Yeah.
Isn't that be helpful because we are doing multitasking right now and we are doing like multi-threading? That be like each thread can put in one line, so that way we can actually have like faster speed for each thread.
Yeah, so the speculation is that you could use separate lines for separate threads, but I want to emphasize, most of you have taken 61B, I assume, right? And so you've done some multi-threaded programming. Threading is a concept that doesn't exist in hardware. Okay, it's a conceptual model on top of what the hardware does. Right? The hardware gives you concurrency by one of two mechanisms today. Either you have two distinct processors, and they're running instructions sequentially. That's a multi-core architecture, or you're using interrupts. Okay, so an interrupt will occur, which means that one of the thread that is currently executing stops executing. It doesn't look like it stops executing because our conceptual model is that it keeps executing, but it actually does stop executing. So suppose that we have only a single core connected on this end, and we've got a serial port link in USB 3. It's about a gigabit per second, okay, coming through. So that means a byte every 8 nanoseconds. You're going to be getting interrupts on each of these lines at extremely high rates. Can you context switch quickly enough to take advantage of that? Probably not. The context switch cost is going to be much higher. So I think that could work if you had multi-core architecture. You had a separate processor on each end of these wires, but it'd be hard to use on where you're multiplexing a bunch of threads on a single core. Right. Context switches are actually quite expensive. They take many, many cycles to execute. Okay. A to D converters, we'll use a lot of those in the lab. And there's basically two different mechanisms for A to D converters. They can be pretty simple, but one is called polling, which is simply that you set up the A to D converter to measure a physical quantity at some rate, and all it does is it measures it and sticks the value in a register. Okay? And then what polling is in your software, you go and you ask the A to D converter by reading a register, a memory mapped register. You ask it, is the conversion complete? If it's not, I just wait. I just spin lock. I just execute nothing until it is ready. The register tells me it's ready. Then I read the value and I process it. Okay? The second mechanism is to use interrupts, which is where you set up the hardware to notify me when the conversion is complete, and then I'll go over that mechanism in a minute, but I would like to take a 3-minute break first, because this would be a good time to do that. Yep.
The question about like if we are using multiple lines is like we had like UART and we always like did other stuff waiting for UART to like send the package over or receive the package. So if we have multiple lines, we don't have to send packages over all the lines, but we can actually like send information a lot faster. So we send one package on the first UART, and then we can send the next package on the second UART.
Yeah, that's in the case of UART. UART's a very slow interface. Compared, as I said, it was designed in the 50s to talk to teletypes, right? So that's why it works. Yes, if these are UART connections, then by all means, yes, multiplexing them in a multitasking context is very efficient.
But if it's like Ethernet cable or something.
If it's Ethernet cable, it's a lot harder to do. Yeah, because your context switches would have to be much faster. Or if it's USB, this USB is about 100 megabits per second. USB 3 is about a gigabit per second. So the speeds are really quite high on today's modern serial interfaces. Yep. Okay, let's go ahead and resume. Just as a last word on memory architecture, I wanted to just show you what the ARM memory layout looks like. It's not that different, except that here, unlike the one we were looking at before, the memory space is used for both program and data, the same set of 32-bit addresses. This is a 32-bit processor with 32-bit addresses. So data words are 32 bits, instruction words are 32 bits, and addresses are 32 bits. Everything's 32 bits across the board, so it's easy to sort of lump them all into the same address space. So the way the memory architecture works in this case is the bottom half a gigabyte is flash. Now, do you think on that little board there's a half a gigabyte of flash? Nah. There's a difference between an architecture and an implementation of an architecture. Okay? The architecture allows up to a gigabyte worth of addresses for flash memory. But a particular implementation will not want to spend that much money, and so most of these addresses will have nothing there. Okay? And obviously a compiler needs to know which of the addresses have something there and which of them don't. Okay, but the way the architecture works is it allows up to a half a gigabyte for program memory, up to a half a gigabyte for data memory, up to a half a gigabyte for peripherals. That's a bizarre choice, but that's what ARM did. Another gigabyte for data memory, okay? Another gigabyte for external devices that are memory mapped. Again, interesting choice, but and then a private peripheral bus. When you see something like that, that means if you write to those addresses, you're going to really mess things up. And if okay, or the hardware may not even let you do that, but so. And then, and then a bunch of peripherals. These are the kind of the built-in peripherals, I guess, for this ARM processor. So you see these kinds of things a lot when you're working at the bare iron level, and you sort of want to get to the point where you can read them reasonably comfortably so that you can get a sense of what's going on. Okay, question. What's your name?
I'm Bert.
Bert.
So how do you know how much physical memory you actually have? Where
It's somewhere in the 1,000 pages of spec sheet that you get along with your piece of hardware. And it can be an interesting exercise to find that information that you need, right? It's not always easy to find. You get good at sort of thumbing through spec sheets and finding what you need, right? Okay, so let's switch to talking about more explicitly about I/O. I've already talked quite a bit about I/O, so I can skip over some things, but the key thing here is that we're dealing with cyber physical systems, and the cyber world is digital and discrete and sequential, and the physical world is not. Things operate continuously. Time is a continuum. We can get into philosophical debates about whether it really is or not, but for practical purposes it is. The physical world is concurrent. There's stuff happening at the same time all the time, whereas the software world tends to be very sequential, and we try to create illusions of concurrency, which have artifacts that become a big issue when there's an interface between these things. But connecting these two worlds is what I/O is all about. So you guys probably know this kind of picture. This is from my living room when Santa Claus brought us Guitar Hero, which ate up a good month of my time after that. But what a fun toy. But anyway, the interfaces here are kind of interesting. I mean, there's a lot going on in a device like that. You've got these wireless devices that have these infrared cameras I mentioned in them, and they use Bluetooth to connect to the base station. By the way, how many of you have played with a Kinect? That's another very cool device, right? That one uses a very different model, right, where the base station is where all the action is, and it's using vision algorithms to figure out what's going on. But in this case, it's using rather simple measurements, accelerometers and an infrared camera. That's what's in that sensor, and a bunch of buttons. And there's a small 8-bit microcontroller in the Wiimote that is parsing the data, reading the A to D converter to get the accelerometer information, reading the CCD array of infrared sensors to read the camera data, and packetizing that stuff up and sending it out as a serial connection over Bluetooth. You can hack it easily. You can use a Wiimote to talk to just about anything that has Bluetooth, and it can be great fun to do it. I mean, most of our laptops have Bluetooth, so you can use a Wiimote to talk to your laptop. You can use it. You can put Bluetooth on anything that has a UART by using there's UART to Bluetooth adapters, and then writing the code for that thing is pretty easy. So one of the projects, the first time we taught this course, the team made a miniature Segway it had two wheels about this big. They used Lego Mindstorms for the physical device. It was just a Lego Mindstorms brick, two wheels with motors driving them, and they steered it with a Wiimote. So they put a Bluetooth connection on it. So you'd lean your Wiimote forward and it would move forward. You'd lean the Wiimote back and it would move back. You'd twist the Wiimote and it would turn. It was amazing. It was a very cool project. Yeah.
Things like the Wiimote, though, inherently HID devices that have some overhead.
HID? What's HID mean?
Human interface device.
Oh, yeah.
Class of Bluetooth, like when you connect to your computer with the Wiimote, it shows up as an HID device.
So this is an issue of software layers on top of this. So what's actually happening is it is a raw serial connection with a protocol overlaid on top of it. So the Wiimote is actually sending out some bytes that are identifying it as a device of a certain type. You can ignore that stuff, right? Or you can pay attention to it, and you know, then you know, you can have it. If your software on your platform recognizes that, it will identify it as a particular device and kind of know what to do with it. More often than not, however, what happens is your device gets confused because it has no idea what this header information means, and you have a devil of a time getting the Wiimote to actually talk to your laptop, right? Because it's having to try to interpret information that it can't figure out. So none of this stuff happens magically, right? If your laptop recognizes a Wiimote once paired, it's because someone has written some pretty tricky software to get it to do that. It doesn't just happen automatically. Okay. So this is the picture of the Luminary board that we used the last couple of years. And here's a picture of a serial connection and a parallel connection and a serial connection. Okay. Okay, so this comes back to your question, Ryan, which is, what if you have a bunch of different devices connected to a bus? Okay, how do you get them from stepping all over each other's toes? Well, the first order line of defense is an electrical issue. You don't want one of your devices to be asserting that the voltage is 0 and another device asserting that the voltage is 5. Why not? You have a short circuit, right? I mean, you want the wires in the bus ideally have fairly low resistance, because if they have a lot of resistance, they'll introduce propagation delays. The bus will be slow. You'll have to consume a lot of power to drive the bus, etc. So you want them to be low resistance. And if one device is asserting 5 volts and another device is asserting 0 volts, they have a low resistance connection between them. The two devices are going to get extremely hot and probably start producing smoke. Okay, that may happen to you in the lab, but we hope not. But part of, we'd like you to kind of understand what the interfaces are and how they work. So an interface to a bus is typically what is called an open collector interface, which as a circuit looks something like this. So you've got a bus here, one line of a bus in this case, and you've got a whole bunch of devices connected to it. And the devices never assert that the voltage is high in this design. Sometimes it's reversed, but in this particular design, they never assert that the voltage is high. They can only assert that the voltage is low. Okay? The way they assert that the voltage is low is they turn on this transistor. So they have a drive transistor that's simply connected to a register. So this register is somewhere in memory, in your memory map. You write to this register. If you put a 1 in this bit of the register, you turn on this transistor. The effect of turning on this transistor is to say, okay, I would like this bus to have 0 volts on it. Okay? I'm connecting the bus to ground. So what happens? Well, somewhere else on the bus, there's this pull-up resistor that is connected to a high voltage. And this resistor here ensures that we don't have a short circuit. Okay? But it'll also allow this voltage to drop to 0. And you will get some current flowing through this transistor, but this resistor is designed so that the current is totally manageable by these devices. Okay? If you're the only device that is asserting that the voltage is 0, then you've effectively conveyed information on the bus. However, there might be multiple devices asserting that the bus is 0, in which case the bus line will go to 0 and everyone will see 0, and you have to somehow disambiguate which one is which. Okay? If nobody on the bus is asserting that it is 0, then what is the voltage on the bus? It's VDD, right? It floats up because there's no current flowing through this resistor. Consequently, the voltage will rise to equal the power supply voltage. And anybody who's reading that voltage will see that it's high. Okay? So that's the first line of defense. Now you can connect a whole bunch of devices to the bus, and they can asynchronously put values on that bus without causing short circuits. Now that's not quite enough to disambiguate because what you'd like to do if you have a device that is connected to the bus and you want it to respond to a certain address. So it's monitoring the address lines. So there'll be a bunch of lines on the bus that say, the current address is such and such, and you're looking for, okay, my address is hex 20. If I get a hex 20, I would like to put my value onto the data bus. The way you put the value onto the data bus is by turning on a bunch of transistors that are connected to the lines on the data bus. And hopefully, if that address 20 is put on the address line, nobody else on that bus will respond to it because nobody else responds to address 20. So if you're the only one responding to address 20, you can safely assert your data on the data lines, and your value will be then visible on the data bus. Okay, so that's one mechanism. That's a simple response mechanism. So if you want to hang a passive device that simply has memory mapped registers, that's how you do it. You just listen for your address. When you get your address, you assert your value on the data bus. Very simple. It's a little more complicated if you have a device that wants to initiate transactions on the bus, because then you need some arbitration scheme. So a bus will typically have not only address and data lines, but it has a few other lines that are used to manage the access of multiple devices to the bus. So one of those lines might be a bus request line. So what happens is you make a request by pulling a bus request line down low. An arbiter, which is a piece of hardware hanging off the bus, notices that somebody pulled this down low, or maybe more than one person did, okay? And it attempts to figure out which one did. Okay, so there's some sort of handshake protocol that happens. One simple mechanism that it might do is it might be that every item on the bus has a unique ID, and they pull down lines, bus request lines that assert that ID, and then the arbiter will respond saying, okay, the one with this ID is the one that's got the bus now. Okay. So the exact protocol there very much depends on the bus protocol. In fact, what a bus protocol is mostly about that arbitration. How do different devices get access to the same bus? Okay. Does that make sense? Mostly you're not going to have to worry too much about bus protocols in the lab, because they tend to be internal to these devices. And the way that you interface with these devices is through this concept of memory mapped registers. And as soon as you understand how memory mapped registers basically work, you don't have to worry too much about the bus protocols. If you get really fancy, for example, if you're in your project, you're going to be doing FPGA designs where you're putting custom hardware and having it interact with the microblaze, then you probably will need to understand bus protocols. Okay. Serial interfaces work a little bit differently. The RS-232 standard is the one that was established to talk to teletypes. Okay, and it persists. It's a really awkward standard, primarily because it's electrically awkward. The voltages are plus and minus 12 volts, which is, digital logic doesn't do 12 volts anymore. So if you want to support RS-232, you have to put voltage converters on your hardware to convert your 3-volt supply to a 12-volt supply in order to be able to drive RS-232 devices. So it's really pretty awkward to actually use raw RS-232. RS-232 is you typically see it on a device with a connector like this. This is one of these DB9 connectors. There's actually, for the most part, there's really only 2 of these pins that you care about: the send data and the receive data, okay, and then a ground line, a third one. But there's a bunch of other stuff that teletypes needed, and therefore is there, okay. These things are mostly being replaced by USB. USB has 4 wires in it. You can look inside the USB connector and identify the 4 wires that are in there. USB is electrically simpler. It doesn't have this awkwardness of plus and minus 12 volts, but it has more complicated protocols built on top of it. So how you use USB, how arbitration is done, you can hang a bunch of devices off the same USB line, so arbitration becomes an issue on a USB line. How all that is done is considerably more complicated than RS-232. RS-232 is simple point-to-point. Only 2 devices, 1 sender, 1 receiver. The sender sends out on the send line, the receiver receives on the receive line. If you get them backwards, no communication happens, right? So you need cables that reverse pins 2 and 3 of the DB9 connector so that the sender is at one end, the receiver is at the other end. So pin 2 at this end is connected to pin 3 at this end, and pin 2 at this end is connected to pin 3 at that end. And if it's not that way, then both devices will try to send on the same line, and they will have a short circuit. The RS-232 interface is the specification in the standard tolerates those short circuits by saying you have to have a certain amount of impedance in your interface so you don't fry the other guy, even if you're both asserting the same opposite voltages on the line. That impedance requirement makes this interface extremely slow. Okay, it goes up to, I think, 58 kilobits per second. That's as high as RS-232 will go. And that's in part because of the electrical connections that tolerate short circuits, okay, which really slows things down. But it makes it pretty robust. You can plug anything into these, and it's pretty hard to hurt your device, right? I mean, if you plug it into the wall, that would probably be a problem. But so don't do that. But they're pretty robust, these RS-232 interfaces, but they're really quite slow. So a UART converts the serial connection. So a serial connection, this plot that's shown here shows voltages over time. And the way RS-232 works is you simply assert a plus 12 volts for some period of time, and that says, I'm starting to send you something. And then you do a burst of highs and lows, okay? 8 of them, followed by 1 or more stop bits, which are lows. Okay? This is completely asynchronous. You can do this at any time. The wire's sitting there idle, and you just do and you've sent out a byte. Okay? At the receiving end, the circuitry is just sitting there listening, or the line's idle, and all of a sudden the voltage goes high. It wakes up. It has to know what rate you're sending at, 58 kilobits per second, for example. So it sees the start line and it says, oh, I better start paying attention, and it latches the voltages on the line at just the rate for 58 kilobits per second to get your 8 bits, okay, and reads those into a register. That's another reason that the protocol is very slow, is that this guy's notion of 58 kilobits per second may not be the same as this guy's notion of 58 kilobits per second. You can't have perfect clocks, right? So the clocks are going to differ. So this guy thinks it's sending at 58, but it's actually sending at 58.001. This guy thinks it's receiving at 58, but it's actually receiving at 57.005. And so this sequence has to be a short, because the receiving is going to clock at this point, then clock at this point, then clock at this point, but its error is going to be increasing relative to the transmitter. And you better stop sending before the error gets so big that it spills over 1 bit period. Okay, because at that point then you'll latch in the wrong bit and you'll get the wrong data. So that's how RS-232 works. It just keeps these things short. Both sides have to agree on the speed at which they're sending. They both have to have clocks that are precise enough to be able to stay in sync for 8 bits, which is not hard these days, but it was hard in the days of the teletype. Okay? And that's it. That's how it works. It's really very, very simple. So these things get latched into a register. So here's a picture of what the hardware looks like. You've got an optional, here this shows, you can use serial links over infrared. The robots that we have, by the way, have infrared receiver and transmitter, that little knob on the front. can be used to receive infrared and send infrared serial data over infrared. So the robots can communicate with one another through this infrared link. People have used that in projects before. But the key is you've got serial lines, which are shown here. Where's the... Yeah, here's the serial out, and here's the serial in. Okay, so this is the hardware that just, as soon as it sees the start bit, it starts latching. And then once it's done, when it's latched 8 values, it sticks those in a register. Here's a device that hangs off the bus. When it sees its address, it asserts the value of that register on the bus. There's all these other interfaces that are used, for example, you can ask it, again, by reading a memory mapped register, ask it whether there's a byte there. Is there a byte for me? You can also ask it to wake me up when there is a byte for me, okay, by asserting an interrupt. These other lines are used for that, okay? So let's talk a little bit about how that works. So in this Atmel AVR 8-bit microcontroller, we can send a byte over the serial port using C code like this. Okay? This is one of these addresses that is defined in a header file somewhere, but it's just a memory mapped register. So what is this doing? Well, it's taking the value of this memory mapped register, and it's doing a bitwise AND with the hex number 20. Why a bitwise AND with the hex number 20? Well, because it wants to look at just one bit of that memory mapped register. That one bit is going to tell it, is there a byte for me? If there is a byte for me, that bit will be 1. If there is no byte for me, that bit will be 0. So this while loop, which is empty, by the way, there's no instruction there, will simply keep executing until there's a bit for me. This is the polling scheme. So this C program just executes forever until that one bit of that memory mapped register goes to 1. At that point, we assume there's a byte for us, and so we read that byte. And so in this case, oh, sorry, this is doing a write. This is writing a byte. So this is not, so this bit must be telling me, are you available to send a byte, right? Which basically means, have you finished sending the last byte I asked you to send? If you've finished sending the last byte I've asked you to send, then you're available. Okay, so you wait until the hardware is available, and then you take the value that you want to send over the serial port and you write it to this memory mapped location, and you're done. It's gone. It's out over the serial port. Not really. It actually is at 58 kilobits per second. It's going to take a while to get out. Okay, that's why you need this while loop here. How long? Assume we've got basically 58 kilobits per second. That means that to send 8 bits is going to take 139 microseconds. Suppose this processor runs at 18 megahertz. That's a glacially slow processor these days, but that's what this particular Atmel AVR ran at. How many cycles does it take to send out 1 byte? Well, if you do the math, 2,500 cycles. Okay? You need this wait, because if you're sending bytes out on the serial port, there's a pretty good chance you're going to get to the point in your code where you want to send the next byte before that previous byte has actually gotten out the door. Is this clear? Yes, question. What's your name?
Dorian.
Dorian?
Dorian, yeah.
Mm-hmm.
So is it possible that you have interrupt between the while loop and the
Oh, yes. You could get interrupted while executing this while loop, for sure. And you could also get interrupted after you've you're finished executing the while loop. It tells you it's ready to send, but before you get to executing this instruction, you get interrupted. What if your interrupt service routine decides to use the serial port? What do you think is the data that's going to go out on that serial port? going to be garbage, right? It's possible that one bit will get out, and then the interrupt service routine, the interrupt service routine will try to send out 8 bytes, right? Maybe one bit will get out of that, of what it sends, and then you return from interrupt, and this guy overwrites the register and stomps over the rest of the 7 bits of the word that get sent out, right? And what ends up getting sent out is garbage. You have to not let that happen, right? So if you have interrupt service routines that are using the serial port, you better make sure to disable interrupts between this while loop and this. Now that could be a problem. Disabling interrupts while you're doing an open-ended while loop means, gee, I could be not responding to the physical world for a long time. Even the reset line, is handled by an interrupt. So that could be a problem. You have to think about these things when you're architecting your software. So, one strategy would be don't talk to the serial port in an interrupt service routine, or do all of your talking to the serial port in interrupt service routines only, okay? And carefully control how they're architected. Think about what's doing what when, and so on. So receiving via UART is similar, except that's what I thought the original code was doing, right? But this is just you're looking at a different bit in that status register. This is potentially much more dangerous than the previous one, because at least this previous one, the while loop is actually bounded by how much time it takes the hardware to get a byte out. This is bounded only by what the external world does. This while loop will continue to execute until the external world provides me with a byte. Well, what if someone yanks the wire out? Okay. The external world's never going to provide me with a byte, and my program is going to be dead. It's just going to sit there in this while loop forever. Okay. You have to think about these things. Okay. So we will... wait, I have 1 more minute, so let's not stop yet. So this could take up to 2,500 cycles to receive each byte. So that's a polling mechanism. Interrupts are quite a bit more complicated and a lot more powerful and a lot more interesting. Okay, you can use the hardware a lot more efficiently, but they're much more dangerous. And in fact, in a lot of safety critical systems, they're simply disallowed. Everything is done by polling. Okay, if you have a safety critical system, you may be forced to do that, because it can get really hard to be guaranteed of being able to control what's going on when you've got interrupts happening. But interrupts are very commonly used, and they can be used very effectively and very reliably, but you really have to understand what's going on. So the way that it works is you do some setup initially, and the setup is basically just saying it tells the external hardware that the way that it should notify me is by raising an interrupt request. Interrupt request is done on one of these open collector lines. Okay, the external hardware pulls the line low, and that's a request for interrupt. And so you tell the external hardware by just writing to a memory mapped register saying, I want you to interrupt me when something happens. Okay. When that interrupt occurs, part of your setup also specifies, it may specify, in a simple hardware you might only have 1 interrupt, in which case in the simplest processor architecture, if there's just 1 interrupt, when an interrupt occurs, the processor will take the current program counter, push it on the stack, and replace the program counter value with a fixed address and start executing code at that address. Okay? So your interrupt service routine now has to be at that address. So whatever you want to do with that external hardware, you put at that address in program memory, and that's what will respond to the interrupt. So we'll talk a little bit more about that on Tuesday, and then move on.